Later on that invites you to kind of mess around with the functions, not the step size, essentially it's the step size and domain range. I want you to use your calculator. I want you to go to polar mode. I want you to use your calculator today. Yesterday was no calculator, today will be mostly calculator.
Do you get to make cards?
Say again?
Do you get to make cards?
Yes, we are going to make cards. We're going to mess around with them and put them upside down, twist them around.
We're not going to twist cards, okay?
Promise we won't on purpose break them. We could break them, I suppose.
Oh,
I don't want to break
I would love to break hearts. Love is dead.
No, love is alive.
Yeah, no, it is.
Love is not a myth.
Love
You just gotta wait for that
just
special
doesn't.
lady.
It's like Santa. It goes away with age.
It's like Santa.
Alright, so R equals 3 cosine 2 theta. You want to be in radian
Over here. Mr. Anderson, tell them that love is alive.
Love is love. Absolutely.
Don't
But
fit
they need to
yourself.
experience that to know that for sure. So we'll figure out this.
Maybe not Logan. He's a
Should
little.
we go Zoom 5?
You can, yeah. You go Zoom 6, Zoom 5. That's kind of small as far as just being able to see what's happening there.
You tricked me with Zoom 5.
It is Zoom 5. It's a square. It makes it look way better.
It's all small on mine.
We could zoom in, I suppose.
Zoom in.
Huh?
Hi. Three and 3 and 3. Sweet.
All right, so I sketched the one up we did yesterday. The rose had 3 petals. The middle one.
Did you guys know? Curious. Did you guys know that there's a SpongeBob musical?
There's a SpongeBob.
Did you know that?
Yeah, there's also a shark one.
There's a SpongeBob episode that's like 3 minutes long about global warming. And it's literally just the entire ocean boiling away.
You're serious? That sounds very depressing.
It is actually pretty
Boiling away.
No, it's pretty, okay, so, okay.
I wish you guys were paying attention. This is probably the single greatest rose I've ever hand drawn so far.
Wow, you are. Don't jinx it yet, Mr. Anderson.
Oh, he connected it very well. He really
Alright, don't mess up with the last one.
Alright.
Just
Stakes
copy
are
and
high.
paste it.
Going very slowly so as not to mess it up.
Solid.
Oh, I'm so pleased with that.
That's pretty good.
Man, that never happens, as you guys know. That never happens.
I wish I could do it with like all in.
Somebody's calling me.
Answer.
Someone's calling your personal phone or your
No, this is like work. I had it open earlier and forgot to shut it.
work? That's what they're calling me.
Work phone. That's right, I need
They
to go
need me.
save some cat out of a tree. No, hey, I have a question for you guys. So, you know, clearly I have enough experience to know what these basically look like. And I do know that if I have a rose, which a rose is going to be like A sine or cosine B theta. I know it's always going to be a rose. But maybe a good question to ask you would be, how on earth did I know that it would look like that? Right? I think there's some things we can bring out here. Any thoughts? Why would it be 4 petals to the rose instead of 2?
Because the even is double. If the B is even, it's double.
That's right. If B is even, the number of petals is actually double that B, right? How would I know that it's oriented that way? How would I know that it's not sort of twisted like the first one we did?
Because cosine starts at 0.
Cosine starts at 0, and when theta is 0, cosine is
0. 3. No, 2. 3. 1.
1 times
Okay,
3 is 3. I kind of knew where you were going
Yeah,
with
I
that,
was
but
like,
yeah.
wait, what's the pedal length? And I just, yeah.
Yeah, the pedal length is 3,
Yeah,
right?
And then,
And
but
I,
it's not that. You said cosine, and then I realized that at the end it's like,
yeah, but of course, I mean, I could tell you were on. I think I was tracking with you. I basically just plotted. I just wanted to know where the end of the pedals was, and so I kind of plotted some of those classic unit circle angles in my head real quick, and realized, okay, it's like this, not this, or some other variation on that. I was able to plot that, and then I drew it better than I've ever drawn those before. So I'm really pleased with that. So then, how many pedals would you guess would happen with that final? While you're on your calculator, it's 5. So if that little b theta and b is odd, then the number of pedals actually matches that number, right?
If it's not odd, it doubles.
If it's even, it doubles. Exactly right.
So there's no way to get
There's no way to get to 2.
2.
Technically, with a lemniscate, if you have a lemniscate, it's sort of a 2-pedaled. Say again?
They're 2-pedal and lemniscates essentially.
Wouldn't you?
Yeah, it's like kind of a 2-pedal flower,
Yeah.
yeah.
You'd have to use.
but it looks different for sure.
You'd have to use 2 functions.
Now with a lemniscate.
Right?
A lemniscate does involve a square root, so you could argue that it's I guess it would be 2 different y in terms of x functions, for sure. If you're going to think y in terms of x, but a lemniscate, you get 2 different r's for each theta, essentially.
oh, that's why you can do
So that's why you only need, we'll talk about why you only need pi to get there. Hey, there's something else I want you guys to notice here. This is pretty crucial here as far as what we're going to be doing with calculus. On your calculator, why don't you enter r equals 2 sine of 3 theta, that first one, and then maybe for your y2, enter r equals 3 cosine of 2 theta, which is the second one. And what I want you to do is I want you to play around with the window. So please push window and set your theta min to be 0 and theta max to be pi. So theta min 0, theta max pi, hit graph, and notice what happens. It's kind of interesting. The 2 that I have up there, the red one and the purple. So when you do that, do you notice how one of them seems to be complete, but the other one's not? Tap.
That's cool. Well, it kind of.
So yeah, enter both of those and go window, and then go theta min 0, theta max pi.
Made a circle.
Or it doesn't matter.
Well, not a circle, but a little bit.
So I think the important thing to notice here is the theta domain, right? So if you just go 0 to pi, you get the whole first rows, right? You get the whole thing. But if you do 0 to pi for that second rows, you only get half of it. So this is another principle with those roses. And what it is if b is odd, you're only going to need pi to complete the whole rows.
That's why the evens have more pedals than
Yeah.
odds.
That's right. And then if b is even, then you're going to need the full 0 to 2 pi to get the whole rows. So why is that important? Well, if you go back to your window, and change your theta to theta min, to keep it at 0, go theta max 2 pi. Let's think about what happens here. If you do 0 to 2 pi, and you hit graph now, don't you get the whole rows for both of them? But wasn't that first rows complete just after 0 to pi? So isn't the graph just retracing it? Just like going over it again, right? Just retracing it. So why would that be important? Well, that would certainly be important when you're thinking about the area. If you accidentally trace the rows twice,
Oh, yeah.
wouldn't you accidentally get double the area? You'd never know it unless you knew this sort of thing. Make sense? So just be careful with your domain. So that last one there, r equals 2 sine of 5 theta. I know it's going to be a 5-pedaled rows. I know that it should only take pi to do the whole rows. It's just a matter of figuring out where these petals are. And of course, the more petals there are, the harder it is to draw. So I'm probably going to butcher this one, especially compared to my purple one. We'll find out. So I know, let's see if I do, pi over 2. Pi over 2 should be an end of a petal, right? So pi over 2, I get sine of 5 pi over 2, which would just be 1 times 2. So I'm thinking that this will certainly have an end of a petal right there. And then it's just a question of, is it going to be, oh boy, I don't know. I'm just going to take, let's see here. Well, I know it's going to be this.
There was a way to find the angle of the first seven.
Oh, there totally is. I just am not feeling particularly motivated. It's when R is 0. You know you're crossing through the pole.
Can't you do pi over 2 divided by b2 to get the angle of the first one?
Yeah, possibly.
I think that's
Yeah, possibly. Let's see here. Negative.
So I know cosine, when you're drawing these, starts at the origin, right? Or starts at theta equals 0. You can get your, can't you get your first petal just at theta equals
Yeah, for sure, because cosine of 0 is 1.
So, okay, so for sine, what's the rule on that again?
I did pi over 2 because I knew that that should get me, depending on what that b is, that should get me to a good place
Okay.
as far as the end of a petal.
Okay, so what's the difference between pi over 2 there and then the pi over 2? Because it didn't do that same thing for the first sine.
It's really just a matter of plotting points, right?
Yeah,
So it came down here
correct.
because when you plugged a pi over 2 there, you got 3 pi over 2, and sine of 3 pi over 2 is negative 1 instead of 1.
Okay, I got
Yeah, that's it. And that's why technology is nice here. So let's see here. Do we, I don't know. Thinking, can't be that. 3 power 2, yeah. Okay, so it's got to be also here, right?
Yes.
No? Is it split in there?
No, it's like a starfish. You know,
Yeah.
like starfish, that's
You
its
know
head.
what, don't give it away.
Oh.
Maybe say
Sorry.
spoilers next time.
Looking at that.
Yeah, yeah, something like that. And then it's got little arms.
Oh boy, I messed that one up.
Because the petals are always going to be equally spaced, right?
Yes.
Should be,
Yeah.
yep. And the arms in the first and second quadrant?
Yeah.
Yeah,
Okay,
Yeah.
fair enough.
totally.
Look at this little starfish.
Oh, too far.
It's beautiful. There you
It even is
Oh, it's
starfish colored
so
almost,
bad.
right? The classic orangey looking starfish. Okay, I think those arms should probably be a little bit lower angled, but obviously technology is kind of nice here when these things get a little more complicated. And this is sometimes where people are like, dude, we could totally make one with like 50,000 petals. Whatever. It starts to just look like this blob after a while. Okay, so just some hints and reminders here. These are things that we can find tangent lines, vertical tangent lines, horizontal tangent lines. Obviously, these would have a lot of those. And I don't know that I would ever give you a question like the orange graph and say, hey, find all of the equations of the horizontal tangent lines. I mean, there'd be like maybe 4 of them, something like that. There'd be a lot of angles. It would just be very laborious because there would be quite a few things to consider. But maybe we would only consider part of the graph, maybe one of the petals of the first quadrant or whatever certain domain might use there. And then, of course, with these roses, a classic thing to do is to try to find the area within the rose or perhaps just one petal of the rose. Important that you know the angles there. Of course, with a rose, don't all of the petals start and stop at the origin? AKA when R is 0. And so finding when R is 0 is actually going to be a pretty critical thing. And when you think about it, if I'm taking stuff like this or this or this, and I'm setting them equal to 0 and trying to solve for theta, what's going to be a big thing? What's going to be a really important skill or fact set?
The unit circle.
The unit circle, aka, or the triangle-y thing, whatever you need to do to be able to figure out theta given some trig equation, that will be a big thing, okay? That'll be a really important thing. So hopefully you're either good at that or willing to review it a little bit to get better if needed. Fair enough? All right, let's wrap up our graphing here, and we'll continue to depend on the calculator a bit for these. So if you would,
Oh, we got some. Oh man.
check these out. This is where perhaps Peyton will be happier, and we will play around with these graphs a bit too. So if you would, please use your graphing technology to try to graph these. So all three of those ones we just made were roses. And notice how these new three are quite different. It's not 2 cosine 3 theta or 5 sine 2 theta, whatever it might be. We've got this 1 plus or this 2 plus going on. And of course, it's going to change the nature of the graph quite a bit.
Oh, I remember this.
Oh man, here we go. I'm going to
So-
try.
Would it be safe to say that as theta approaches infinity, you get closer and closer to just a filled-in circle?
Yes.
As theta?
Oh, no, sorry, as B, my apologies.
Oh, back to the roses?
Yeah.
Sure, yeah. But of course, even if B was like 10 trillion, if you just zoomed in enough, you'd be able to see the space within each little petal. But yeah, I mean, certainly at a certain zoom level.
B approaches infinity.
But yeah, if you say limit as B approaches infinity, it becomes a solid circle. I can live with that
I'm just trying to
description.
think about the most inefficient way to find the area of a circle.
I thought that can sometimes like doing it like that is actually the most interesting. So I wouldn't shy away from that.
So would you just measure the arc length as the limit approaches infinity of each like strip?
No, I guess you could do the arc length, but also you just find the area of the petals in the same way you find the area of a rectangle.
You need to
if you're doing
multiply it by-
line, so.
And the way that you find the area of a petal is actually based on the area of a sector. But of course, as the number of petals approaches infinity, it just becomes essentially a line.
Yeah, I was gonna say the
A
lines
radial
get
line
close
itself.
to each other.
Right.
So if the lines get really close to each other, then the arc length would make up the area as well.
Yeah.
Oh, that's
Interesting.
fun.
Interesting question. Because the arc length would just be essentially a single line segment.
Yeah.
And if you added up a bunch of those,
To
you'd have
infinity.
the area.
Yeah.
Hmm.
So okay, so the area of this. Okay, because I guess the
Look at what I made.
the area of the petal equals the arc length because if you think about it, the space between or the space of the petals
What if I make it
gets
50
infinite
petals?
This is
to that
pretty
as
big. Look at
well.
that. Look at that.
Yeah,
Inside and outside of the petals.
right. Yeah, the outside little, whatever shape you'd call that, gets squeezed down
Yeah.
too. Yeah.
That's just really weird to think about.
Yes, it
What
is.
I'm doing.
That's pretty sick.
Yeah, that's a really interesting question.
He's gonna be thinking about that one for
I like it.
a while.
No, I like it. That's
You
kind
like
of
that question?
yeah. No, nobody's ever really put it that way. It's an interesting thing
I
to
was
think
thinking
about.
about, because I was just making like fun roses.
Yeah, and it just keeps like adding more and more and more and more. Yeah.
I was like, this is
I'm sorry. I think the middle one goes off the graph, doesn't it?
Yeah. I mean, Jack. I mean, you could essentially set that equal to pi or squared. I wonder what you could do with those formulas.
probably some really useless math. Or maybe not.
I mean, we thought useless math. I mean, imaginary numbers helped us get to the moon, allegedly.
Fair enough.
We didn't.
All right. So I did the first two. Obviously, my purple graph in the middle is pretty lopsided. Sorry about that.
Just do this on our calculators. We did that one.
Do what on your calculators?
Just like type in random equations and see if you can make the cool stuff.
We're not going to do that today. Feel free to do that if you want. That's a pretty deep rabbit hole, though, for sure. Okay. So the first two.
Some polar graphs can really spiral out of control.
Nice. So let's see here. This.
Thanks, guys. I'll be here all week.
Hey, guys, I'm going to have you mess around with this a little bit. This one right here, as far as the name goes, this is called a looped limacon, and the C has like some funny little lima. Oops, that's supposed to be an A. Limacon. The C has some little accent symbol on it that I'm not going to write. Yeah, looped limacon. What about the purple graph? Cardioid. So this one happens to be upside down. Cardioid. So obviously it sort of looks like a heart, right? Yeah. So I do kind of want to fiddle around with this cardioid somewhat. I want you guys to see what happens when you play around with the cardioid somewhat. So would you guys also in your calculators, well, I'm just going to graph this right on top. Would you guys also graph R equals 2 plus sine? So same thing, except instead of 2 sine theta, it's 2 plus 1 sine theta. It's going to change things a little bit.
Will we have to memorize like what makes what, like what equations?
No, I'm never going to say, hey, is this? I'm never going to give you an equation and say, what's this the graph of? Mm-hmm. Never going there. I think it's very useful that you be able to say, for you to be able to look at an equation and say, oh, that's a rose. Even if you might you maybe don't know exactly how it's oriented or that sort of thing, but if you're like, that's a rose, or if you look at it and say, oh, it's A plus B cosine theta, that's one of those limacons, cardioids, something like that.
To like differentiate between like those two.
We're going to kind of go there a little bit in class, but I'm not going to make that a point of emphasis for assessing stuff.
Assessed over that.
No, we're not going to like play like a matching game or anything like that.
Great.
No.
Or like no calculator section, you're given an equation and you have to graph the entire thing.
Yeah.
No, so like more often than not, you'll either be given a calculator, given a graph, or it really just won't be necessary at all for you to know the graph. If that makes sense.
I gotcha.
Okay.
Hey, so did you guys get,
And then I just kind of
for this new graph, did you get something like that?
It's just kind of flat.
It just, flattens out a little bit, right.
Really boring.
So the blue one is actually called a dimpled limacon. Okay, so it's not a full-on pointy cardioid where it's got like that sharp point in there. It just kind of flattens out sort of and has more of a smooth transition, but it definitely flattens out kind of. We can explore that a little bit. The key there is that the A value is bigger than the B value. That's what makes that a dimpled limacon rather than a cardioid. And let's do one more here. I'm just messing around with this same one. Let's do R equals 2 plus 3 sine theta. So I just changed that B value from a 2 to a 1, and now it's a 3. And this should look sort of familiar. It is going to go off the top of the graph a little bit. Should look something like... Oh, I was... No, shoot. I was doing so good. I think it's going to do this. I think it's actually going to kind of go off the top of the graph even a little bit more. Did you get the looped limacon again?
Yeah.
Okay. So that's back to being a looped limacon. So I would say that the cardioid and the dimpled limacon and the looped limacon are all kind of in the same family. It's just depending on that relationship between the A and the B, like which one's bigger, essentially.
So we got cardioid because A and B were the same.
Say again?
We got the cardioid because A and B were the same.
Correct.
Okay.
Exactly. Exactly right. Again, to Logan's point, we're not going to play some card match where I give you an equation and I give you a graph and you're supposed to like be able to have these perfectly matched up or named or anything like that. I think it'd be great if you saw something like this and you're like, oh, it's one of those like limacons or cardioids or something like that. Or it's definitely a rose. And I don't know exactly how it's oriented, and so I'm not totally clear on every detail, but I do know that it's a rose. I think that would be very helpful.
Because you would have like some general idea of like what it should look like once.
Yeah.
Okay.
And that way you'd know if you did something wrong, you're like, that is not realistic
That's
at all.
not what it should look like. Yeah. Okay.
And then you could go back and fix it. Or you're like, that's kind of what I was expecting. I'm feeling good.
Yeah.
Yeah.
Awesome.
Okay.
It's actually really ironic.
Hey, I'm not going to put this up on the screen, but speaking of like playing around with this, would you guys maybe do one or two more here, except instead of 2 plus something sine theta, go 2 minus?
It makes it the right way.
The heart is the right way. There we go. Now it actually looks like a heart. So that is true. Like it'll basically just kind of flip it around, reflect it, I guess you could say, and you get a more classic heart-shaped
Yay.
graph.
Jack, did you get it? It literally makes an E.
That's hilarious. Wait. Let's make this.
Change it to tangent from sine. It's really whack.
Yeah, tangent's whack, dude. Tangent's wackadoo. Wait.
Does tangent look? Oh, tangent looks kind of.
So you guys get this this last one?
Whoa. Yeah. That's the one where it's 2 of them.
So that one, yeah, if you're going to put that in your calculator, you do have to put it in as 2 separate equations. One, the plus side, the other one, the minus side.
That's why. There it is.
That's it.
And this one, well, so let's talk about this. I don't know how much you noticed this. Maybe you didn't pay too much attention. That's fine. For the loop limacon, to complete the whole thing, you needed theta to go from 0 to 2 pi. And you also needed the same thing over here, 0 to 2 pi, for the cardioid and the dimpled limacon, the loop limacon. They all need 0 to 2 pi, or 2 pi.
Will it always be a factor of pi that we have to figure it out by? Like for the...
Well, not always, because you can have some really crazy graphs. Like, I don't know if you guys have started doing these sorts of things, but you can also have graphs where it's like r equals theta plus cosine 3 theta. Like, you start putting addition in there, that's going to start messing with that idea, because then you're going to start to get graphs that don't have a nice closed figure like that. And so then at that point, you're probably not going to say, hey, and we have the whole graph, because the graph's just going to continue on forever and ever.
Yeah.
But of these classic type graphs, yeah,
Okay.
I would say
Is
so.
that the scope we're going to be working in? Is just kind of the classic one?
Yeah, for the most part. I mean, I can think of some old AP questions where they even had some of that theta plus something, but then you were given a graph.
Yeah, okay.
It wasn't like, well, come on, you should just be able to come up with this. It's like, well, we know this is sort of out of bounds, so here's a graph.
Okay.
Now do this stuff. Yeah, it won't turn into a, hey, can you plot all these points in 10 minutes or less and then do something with it? I mean,
Sweet.
not going there. That just, if we had unlimited time, we probably still wouldn't do that. Say again?
Mine like graph like that, and I did plus and minus.
Okay, yeah, so go to your window and go to your theta step. So basically you just didn't drop enough breadcrumbs. So make your theta step smaller. What is it right now?
0.1.
So go like 0.05 or something like that, 0.05. And you should fill in a little bit more.
Yeah, still, Mr. Anderson, mine's just skipping, like,
Now that's what mine looks like.
well,
Let's see.
I did the,
How, did that help a little bit?
Yeah, a little bit.
It helped a little bit. You just need more breadcrumbs.
Anybody got anything
like
wacky?
mine traced over it twice, so like I did plus and minus, but even with like, if I just cleared the minus one, it would just do the whole thing. Please wait.
What else is fun?
It like did
It's
the
thinking.
whole,
So,
it's gonna.
did you make it 0 to 2 pi?
See if there's anything.
Yeah,
Okay, hang on just a second. Go back and restart. I want to point out what it's doing.
okay, restart it.
Yeah, I don't know if it'll restart or not. Okay, so it should be tracing down here right now, but it's not. It'll show up over here, right?
Yeah.
So that's 0 to pi, and it should be tracing over here at the same time. and now it gets over to here. Yeah, because you have it set to 0 to 2 pi. So here's the deal. Like if you were going to plot points here, here's the mechanism for how these work. So let's say I did theta equals 0. Right, so I made a table. So if I did theta equals 0 and my r, well, wouldn't I do r squared equals 9 cosine of 0? And r squared then equals 9. And then I would square root both sides. Now, whenever I square root both sides, I'm essentially asking myself, what number squared is 9?
3 and negative.
And the answer is, yeah, plus or minus 3. And so with that, I'd have to say that there's actually, when theta is 0, there's actually 2 points being put down. So just by plugging in theta equals 0, I would get this point here and that point there.
Okay, so it should be like, I'm not coordinated enough to, like, you know what I'm saying, like go like that and then
Yeah,
go to the
totally.
middle and then switch.
Yeah, so then when you're, I'll just, one more illustration, just sure all makes sense. When I'm pointed this yellow, hopefully this shows up, this yellow direction, I would get that point right there.
Yeah.
And then I also should be picking up that point there, again, because of the plus or minus that I'd need to do. Because you doubled your domain, it's tracing it over again, and it's catching the bottom. What's weird about that, I'm just trying to think about what it's doing. Oh, that should be 9 cosine 0, sorry. What's weird about that is if you did plug in, yeah, you should be getting some imaginary stuff going on. Could you be square rooting some negative radii with that 0 to 2 pi? So I don't exactly know what your, I don't know what your calculator is thinking there, to be honest.
What are you thinking?
It's doing something and it's making it look pretty good, but what's happening in there, I'm not exactly sure.
Calculators are weird,
Mr.
man.
Anderson, I made a graph with a bunch of dots.
Yeah, I did that.
It's still graphing.
Yeah.
How did you do that?
I did.
It looks like something my 4-year-old son would do if he got a hold of my calculator. Just
I did E. to the
buttons,
log of
buttons,
ln
buttons.
and, V over theta.
Yeah, we're going nuts out here.
Sine of the e to the log of the ln of sin theta.
Yeah, that one.
Okay, so we have kind of played around with these. You guys have played a little bit more than I have. So I want to for sure focus on people. Listen, I want to focus on people, and this could be all of you, that either never really saw this before or you saw it before and been a while and now you're really rusty. How are we feeling about basically this question? Like, what are these graphs and how are they made? Like, that would essentially be the question I'd pose to you. Are you feeling like you're starting to get like the how are they made and what are they? Or maybe not. Is there further explanation I can give? I can think of at least one thing I could say. Please say something. Give me a thumbs up. Say, I'm getting it. Or, I'm somewhere in between. Or,
Somewhere in between.
I'm
It's fine.
remembering things.
okay.
It's a bit newer.
Let me,
It's a bit all new, so it's a little all.
Oh, yeah.
Just,
Let me-
just all. So,
let me take a second. I want to do something here.
It's only the hardest thing that you did.
Let me focus on, hey, you guys okay with this? I'm going to focus on the red graph. The one that disappeared, the one that's not up there anymore. And let's kind of mentally plot some points. And again, I'm going to draw a little bit more in on this one. We'll see if we can, again, try to understand what's happening. So you tell me, if theta is 0, what's r?
3.
It's 3, right? Because you just do 1 plus 2 cosine 0, 1 plus 2 is 3. So what that means is when theta is 0, the length of the radial line, which I'm representing as a dotted line, is 3. So I'm pointing straight right, and the length is 3. Make sense? Okay. So what happens if I plugged in, say, we'll do pi over 6. We'll kind of do it similar to what we did last time. Pi over 6 would be?
1 plus root 3.
It would be 1 plus root 3, because it would be root 3 over 2 times 2, and the 2's would cancel. So root 3 is about 1.7, so this would be 1 plus that, so it would be about 2.7. So when I am facing roughly this angle, pi over 6, I'm not going to be all the way out there at 3. I'm going to be at about 2.7. So all that's really happening here is that as theta makes its way around its domain, the radius is changing length. Okay, how about pi over 4? What's the output there? 1 plus root 2, and root 2 is about 1.4. So this would be 2.4. So I'm thinking right about there. Give or take? How about pi over 3? This is the easiest one so far.
2.
1 plus 1, right? It's 1 plus 2 times 1/2. Yeah, so 1 plus 1. So pi over 3, we're pointing roughly there. And we're out there at a length of 2. So again, I'm hoping that you can see how all that's really happening here is that the length of the radial line is changing based on the angle that we're pointing towards. Finally, for this part, how about pi over 2?
1.
1 plus 0, right? Yeah. So we would be right there when it's pointing straight up. Interesting. So what I could then do is I could connect these with as smooth of a curve as I can. That's not a very smooth curve. It obviously really bends there. Something like that. Your calculator did a better job of that, of course. So then, where does that extra little loop come into play? Well, we have a little bit to go here in the third quadrant. How about, let's see here, it would be 2 pi over 3? No, wait a minute, sorry. Yeah, it'd be 2 pi over 3. Yeah, 2 pi over 3.
-1.
Right. Times 2.
0.
Plus, oh my gosh. So when we are pointing roughly this direction, roughly, the radius is 0. So it's kind of hard to see the radius there, but I know that we're right there at the origin. And if we plotted all these little in-between points, we'd see that it kind of dips over there for just a short time and comes back right towards the origin. So right now oh goodness, come back. Right now we're facing this direction and the radius is 0. So where does this little extra loop on the inside come from?
Negative.
Well, wouldn't it come from all these angles? And all those angles should represent a negative radius. Okay, so how about one of those angles there would be pi over 4, or excuse me, pi over 2 plus pi over 4, so 3 pi over 4. What's going to happen there?
One minus root 2.
1 minus root 2, and of course root 2 is about 1.4, so this would be 1 minus, so this is going to be negative 0.4.
Negative 0.6-ish.
So it'd be 1 minus, no, it'd be 1 minus 1.4.
Let's consult the calculator.
Should be negative 0.4,
Negative 0.4. Checked it.
right?
Calc.
Okay, so
You know what?
How do you go back to?
so then when I'm facing this pi over 4, I'm actually going to be right, oh, come on, computer, right about there, right?
Yeah.
Okay, how about, it'd be 5 pi over 6. I'm pushing you on your unit circle right now for a reason.
That's
over 6.
yeah.
I don't know.
So it's almost to pi, right? 5 pi over 6.
It's gonna be 1 minus root 3.
So
1 minus root 3. And so that's basically 1 minus 1.7-ish. So when I'm facing this direction, roughly, I got to go backwards 0.7. So that's right about there. So I'm going to switch colors on us and try to trace this a little bit more nicely. So far what I've got is this lovely graph that's come around through here, and now we're all the way to there. Still making sense?
Looks like a hook.
Yeah, so far it looks like a hook. Now what about pi? What's going to happen there?
It's gonna go to 1
It's going to be 1 minus 2,
or negative 1.
so it'd be negative 1. So when I'm facing straight left, I'm actually going to go backwards 1, which would be right there,
Funny how that works.
which would put us on that little part of the loop. And isn't this about where the loop, that little extra loop, wants to turn around? So I'm guessing as we did roughly this much of that third quadrant, we would get a similar pattern up through about there, where we'd be putting down points here, and then eventually back to here, and you can see how that little loop would be completed. Does that make sense? So especially, like Nick and Julie, you guys were really expressed yesterday, man, I kind of didn't really do much with this ever. Does this help seeing the radial line lengthening and shortening?
Yeah.
I choose to do this in the sort of low-tech way. There's some cool stuff on Desmos where you can see some rotation and the length of the radial line getting longer or shorter as it rotates, or backwards or forwards.
Fun.
And if we're still kind of struggling with that in the coming days, maybe we'll turn to that. I kind of like this. It's not exactly breaking spaghetti noodles. Anybody do that in pre-calc?
Wait, no.
So this is a classic way to do this, like as a craft, is you get spaghetti, like dry spaghetti noodles, and you measure them, and you use them to represent and you break them off at the appropriate length, and you use them to make the little radial lines, and then you just trace the end of the spaghetti noodles. I did that a long time ago. I mean, it works. Whatever. It is. Like if you have like a whole class, it takes a while. If you have like an entire class to graph one polar graph, it works. But I don't know if we have that kind of time. Anyways, where do we stand? Are we ready to move forward a little bit? We're not going to move all the way forward, but are we okay with basically the questions of what are they and how are they made? Those would be the two basic questions at this point. Okay. So some of the directions that I was giving you guys as we were going through these are here, and I'll just leave these up to you to kind of play with as you want. But basically, what happens when you play with the theta domain? You make it, 0 to 2 pi, 0 to pi, whatever, or even 0 to like pi over 4, pi over 3. You're just going to get parts of a graph, perhaps. And then that last little bullet point there is one important aspect. You want to make sure that you know when the graph is retracing itself. Because if you're trying to find area and you accidentally do that, you're going to get too much area. Or if you don't go all the way, you're going to get too little area. So just be aware of the fact that domain matters. Okay. I think the timing here is awesome. We are going to do just a little bit of talk about this. And then tomorrow we're going to come back around to this. So please don't feel compelled to think, oh man, by the time I leave this class in 5 minutes, I better have this completely, totally mastered. I mean, if you do, that's awesome. But if you don't stress. We're going to come right back to this and revisit. So check this out. If I have something like this, R equals, Julie and Nick, you guys are going to want to catch this. At least, even if you don't have it mastered, you're going to want to at least start to think about this. Tomorrow we'll come back to this. So if you have some polar graph where it's R in terms of theta, right? So like R equals f of theta, whatever that f of theta happens to be, could be simple, could be complicated, we don't know, but we might have something like that. We can find, as I've told you a couple times, we can find the slope of the tangent line, just like you found starting way back, two graphs like this. Something important to note here is that the slope of the tangent line is always dy dx. Just because you have r's and thetas, or like in December you had t's and x's and y's, the slope of the tangent line always going to be dy dx. So it comes down to how on earth are we supposed to relate this? So I'm going to give you kind of a basic look, and then we'll go a little bit deeper with it. So I told you guys before that polar graphs are actually parametric graphs. They really are. Those old parametric graphs, we had x was in terms of t, and y was in terms of t. So we said the parameter was t. We're going to find out with these that the parameter is going to be theta. So this is just a different version of a parametric graph. So because of that, the way that we can find dy dx is really the same. So this should look really familiar to you all. Dy dx would be dy d theta, and what would you guess would go in the denominator? Yay, so it's just like those old parametric derivatives that we did in November and December. Okay, so where this gets challenging is dy d theta. If I'm going to find dy d theta, don't I need y in terms of theta? And don't I need x in terms of theta? Right? If I'm going to find dy d theta, I need to have y equals blah, blah, blah theta. And I don't have that. I have r equals f of theta. But how do I convert it so that I've got x and y in terms of theta instead?
Y equals r sine theta and x equals r cosine.
There it is. That's where you would start. You'd say, all right, I know what my r equation is, but I've got to go x equals r, which I'll just put here as f of theta times cosine theta, and then y equals r times sine of theta. Okay. So like I said, I'm gonna wrap this up right now, but please don't let this stress you. If I'm gonna find dy d theta, wouldn't I just be using this? What rule would I have to use to find dy d theta? My product rule. There you go. So here it is. 1 d2 plus 2 d1.
Is it dy dx or
This is dy dx. So I'm taking this right here. I'm just adapting this now. And then if I'm going to find dx d theta, wouldn't I just have to use the product rule again? Except this time with the x equals. So it would be 1 d2 plus 2 d1. Please resist the urge to do bad things with cancellations. Nothing cancels here. Nothing cancels. Please resist that urge. But we will completely rebuild and revisit this tomorrow. I just thought I'd throw this at you just to let you know kind of where we're going in the next couple days. Have a great rest of your day. We've kind of, we briefly did it right now. Yeah. Tomorrow what we'll probably do is we'll talk about, how are we actually going to use this thing? Okay. And to be honest with you, I found over the years that some students have found success with taking that right there and just memorizing it. I found that more students have had success with understanding why it works and then just essentially customizing it each time. It's not going to save you a ton of time to memorize it. Yeah. Because it's still quite a bit of writing. So I would leave that part up to you for sure. But we'll just practice using it several times tomorrow. Great. These questions don't take 2 minutes. Yeah. There's going to be a couple of instances where we'll work really hard the whole class and we'll do maybe 2 questions the whole period. Sure. Just because we're going slow and making sure we're doing it right.
Just don't do it on a test. Don't give us a 2-question test.
I know. Well, it could happen. You never know.